Okay, so welcome back to CE 528. We're talking about the optimization problem lab, which is this one right here. Okay, lab optimization problem. And this lab is due on the 24th. So it's not due until 24th at 8:10 a.m., which will take us to the Thanksgiving break because we have the whole week off. But I want to make sure that, you don't have this hanging around your neck as you get ready to eat your Thanksgiving dinner. So make sure you get it done by Wednesday morning. And the plan would be to make sure that we know what we're doing here. The lab itself is, it's relatively straightforward. I think there is an Excel sheet. We're trying to solve an optimization problem, and then and we're writing some brief description about it. Okay, so here is the thing. So if you go to the details here, so you can find all the details. You can find the objective function. So basically what's happening in this problem, and I should probably open this up here. And I'm going to stop share, and I'm going to go ahead and share my entire screen. I'm opening up this Word file here. And it talks about some of the stuff that we talked about in the lecture about the algorithms and stuff like that. And then linear programming is one of the methods that we use to solve these optimization problems. And some of the earliest large-scale applications of linear programming in transportation were made by the leading oil companies who wanted to intelligently manage a far-flung operation and physical distribution system that included oil fields and refineries. So what they needed to do was they needed to get that petroleum product from the oil fields to the refineries, and they had pipelines, and we wanted to figure out how much stuff should go from the oil fields to the refineries, and how much product should be pushed out on each of these refineries. Okay. Linear programming analysis is fairly common. It's spreadsheet tools like Excel have that. So I have a pre-specified linear programming model that I've already provided to you in the Excel file, and I can quickly show it to you. But it's not fully complete. It's 99% complete, but it's not fully complete. So you might have to write down the model specification and make some changes to the model structure. Okay. And the goal is to get you a little bit more comfortable with the linear programming problems that are implemented in Excel. Okay. So this is sort of what you're trying to do. You're trying to go from these oil fields to these refineries. So obviously, pipelines are not necessarily the only system, right? So you have the pipeline, but then you also have tankers, oil tankers, and you'll have railroads in the mix as well. But obviously, to understand the linear programming principles here, we are doing a little bit much more of a simpler job here. And our job is simpler in the sense that it's just taking a spreadsheet that models the simple system. And that simple system is just, your oil fields, your pipelines, and your refineries. Pipelines are common carriers. They're independent companies like railroad that sell the transportation services. So what happens is there will be an oil company that owns the oil fields and the refineries, but the pipelines are owned by a separate company. Okay. So what you have here is that this pipeline 1, 2, 3, 4 are your 4 common carrier pipelines. They connect the region where oil fields are located, and in the vicinities of oil fields and the refineries who are owned by the petroleum company. And then you have where the single lines cross are switching locations where the product can be routed into either outgoing pipeline. So basically, if you come in from here, you can, so if you're coming in from this location. So let me go ahead and spotlight that a little bit. So let's say if you're coming into this location and you get here, so this is sort of like a node where you can push the stuff out to refinery number 1 or to refinery number 2. Right? So you could potentially do that. And same thing over here. If you were to come here, you can put the stuff into refinery number 2 or refinery number 1. So what you need to solve for is find the most profitable method to extract, transport, and refine the petroleum in the given system. So your decision variables are how much petroleum to extract from these 4 refineries, how much product to push in these 4 pipelines, and then how much product to refine at these 3 refineries. Okay, so those will be your decision variables. And then obviously the cost per million barrel of petroleum obtained in oil fields 1 through 4 is 9, 8, 7, and 6 million per million barrel. Okay, including the local distribution cost. And then you're giving some shipping cost. So whatever stuff you ship through these pipelines, there is 1, 1.25, 1.25, and 1 million barrel. And then at each of these refineries, you make money. You sell the product. You sell your raw crude oil to these refineries. And the market value as each of these refineries is 15, 12.5, and 10 million barrels. Now, again, think about this. If you did not have any constraints whatsoever, what would happen? You would want to produce at this 6 million per barrel, the lowest cost pipeline, and you want to sell it at refinery number 2 or refinery number 1, where it fetches you $15 million per million barrel. Does that make sense? If there were no constraints, you will do all your production at number 4 refinery or number 4 oil field, and you will push all your product. You'll push all your product to the least cost of pipeline, maybe pipeline number 1 or pipeline number 4, because they cost the least amount of money. And then you will sell all of your product at refinery number 1, right? If there were no constraint, you will go for the cheapest possible production. You will switch over to the highest possible location where you can get the most price for your oil, and you will ship it through the cheapest pipeline. That makes sense? Give me a quick thumbs up, please. That makes sense. If there were no constraints, right? But that's not always the case, right? Thank you for the thumbs up here. Appreciate that. So if that's not the case, then what do you have to do? You have to, but there are constraints here. So let's look at what those constraints might be. Here is the constraint. The maximum amount that can be produced at each oil field is only 50 million per barrel per year. 50 million barrels per year. So the oil field can only produce 50 million barrels. The maximum amount that can be refined at each refinery is only 125 million barrels. And then the maximum amount that can be shipped through each carrier pipeline is only 75 million barrels. So these are the things, these 3 items act as your constraints. Okay, and these constraints will force you, force your hand in how much stuff you can ship from one location and how much stuff needs to go into each location, because each refinery cannot handle more than 125. And then maximum amount that you can ship through each common carrier pipeline is only 75 million barrels per year. Okay. So there are 3 sets of decision variables, not 3 decision variables, 3 sets. Okay. 3 sets will be PI, annual production at each oil field I. So there are 4 oil fields, as you remember. There are 4 oil fields. So P1, P2, P3, and P4 are your 4 production variables. Okay. RJ is the annual amount of petroleum sent to each refinery. Okay. R1, R2, and R3. And we know what the constraints are on these values. P1, P2, P3, and P4, each of these individually have to be less than or equal to 50 million barrels. Okay. Refinery 1, R1, R2, R3, and R4 have to be less than 125, less than or equal to 125. And then Fk is the flow amount. F subscript K is the flow amount, the annual amount that can be shipped through each pipeline. So you have constraints of F1, F2, F3, and F4. Each of them individually have to be less than or equal to 75. Okay. Now, I'm going to tell you that these are not the only constraints. These are not the only constraints. Yes, these are important constraints and you're going to have those, but these are not your only constraints. You need to be able to write more constraint equations because there are some what we call conservation of flow constraints. Okay, there are some conservation of flow constraints. That means that, if no flow is getting lost along the way, you have to make sure that all the stuff that comes out of the oil fields gets to the refineries and so on and so forth. So there is going to be some constraints related to conservation of flow here. And those are your constraints here that I write down. Okay, so I talk about the conservation of flow constraints here. The LP problem consists of an objective function which calculates for the profit, market value of output from the refineries, minus the sum of oil feed production cost and the pipeline transportation cost. Okay, so you'll write this down as your objective function. And then a collection of constraints which shape the solution. Okay, the constraints reflect the conditions specified above, as well as the conservation of flow constraints. Okay. Now, if you look at the conservation of flow here, to replicate the conservation of flow, you need to come up with like two artificial unknowns. There are R2A and R2B, which represent the amount of petroleum shipped to refinery through the top pair and bottom pair of pipelines. Because if you look carefully here, pipeline 2, see, all the production field have only one output, only one place of getting output. All the refineries have only one place to get input, but this pipeline 2, or I'm sorry, refinery number 2 is actually getting input from these two locations. Okay, so you need to somehow represent that, and that will give you some artificial constraint here, two artificial unknown R2A and R2B, which represents the amount of petroleum shipped to refinery 2 through the top pair and the bottom pair of pipelines respectively. If you look carefully here, okay, so this node, whatever is coming from F3 and F4 have to be distributed to R2 and R3, but you have to make sure that the total amount of flow that goes into refinery 2 R2 is the summation of this one and this flow, these two inputs. All the other ones have only one output and one input, but this refinery 2 is sort of the odd one out, which has two different inputs that come in. So you have to say R2A plus R2B has to be equal to R2. That's your constraint. And then obviously P1 plus P2 equal to F1 plus F2. You can see that here because P1 plus P2 have to add up to F1 plus F2. P3 plus P4 has to add up to F3 plus F4. So that's your, those are your two constraints, conservation of flow constraints. Okay, so these are these two constraints. Okay, and then R1 plus R2A equal to F1 plus F2. Okay, R1 plus R2A, R1, refinery 1 plus R2A, the one that comes here, has to be equal to F1 plus F2. And then similarly, R2B, this is the R2B plus R3, R2B plus R3 has to be equal to F3 plus F4. F3 plus F4 is flow that comes out of here, and that has to be equal to R2B plus R3. So those are the constraints I write down over here. So what I want you to do is, I want you to review all these constraints and then look at then look at this Excel spreadsheet that I've also provided to you. If you go back, if you go and open this optimization Excel sheet, right. So here is this Excel sheet that you could potentially see, and I'm going to go ahead and enable editing here too. So what we are doing here is that we have given you this P1, P2, okay? And these are the cells of my decision variables, okay? And you can see that I have all the things that come into my constraint equations. I have P1, P2, P3, P4. I have R1, R2, and R3. But then I also have R2A and R2B as two additional constraints because they showed up in that equation. And then F1, F2, F3, and F4. And these coefficients are basically creating those matrices. And then these are the right-hand sides of the constraints. Okay. And then this defines my flow value. And then this is not complete. I have some values that are missing here. Okay. And some values that are missing. Okay. So you need to make sure that you put that in, because the cost of refinery at the money that you can get at R1 and R2, R3 are not zero. So you need to make sure that you can put the correct numbers in here. Okay. And then F1, F2, F3, F4 are not zero. There are also costs associated with that you need to input as well. Okay. So what I want you to do is I want you to review the Excel sheet. The Word file that I provided. But then even before that, one more thing that you need to do is that I've made available a YouTube video. If you go back to the lecture that we were talking about in terms of optimization, if you go on down there. So if you go to solver for transportation problem under the optimization tab, solver for transportation problem. So this is the tutorial that will teach you how to use solver. And this is where I set up the transportation problem in the Excel file. So I think that will give you some idea about how this sheet works. So your steps for going through this would be watch this transportation problem using solver video, go through the Word file, and then edit the Excel file, and then follow the steps in the Word file for solving your problem. And obviously I'll be here till 11 o'clock. So if you have any questions, please let me know. And I know some of you had asked for extension for the last lab. So if you want to work on this, that's fine. But I want you to make sure that you are clear on this optimization problem lab before you move on to working on that lab. So I want you to, while I'm here, focus on this particular lab that I'm assigning today. Make sure that you're clear on this lab, and then take the time outside of the lab to finish up your work. Does that sound like a plan? Okay. So unless you all have any questions, I'll pause and we'll go. I'll let you guys work on this. And yeah, if you have any questions, let me know. I'll be here.